Hey folks, we're back. Hopefully you can go ahead and see my screen. We are back to this discussion of, right, we're still in our CCNA initiative and we're still talking about spanning tree protocol concepts, right? And so we went over, right? I believe we checked off everything off the list that has to do with discussing what spanning tree is, right? So, right? With the great thing about spanning tree, of course, performing loop prevention, right? There's always room for improvement, right? And so another protocol was created, right, to improve spanning tree, which is called rapid, right? STP or rapid spanning tree, right? And so if you look at the screen, right, there are a couple of things um, that compare and and let you guys know as readers, right, as new people that are learning about networking, how you know rapid spanning tree compares to spanning tree, right? Rapid spanning tree and STP elect the root switch using the same exact rules and tiebreakers, right? So you guys don't need to relearn that, right? You guys already learned that previously, right? Rapid spanning tree and spanning tree switches select their root ports with the same rules. You guys already learned that. You guys do not need to relearn that, right? Rapid spanning tree and spanning tree elect designated ports on each LAN segment with the same rules and tiebreakers. You guys already learned that, right? You guys already learned that, right? Rapid spanning tree and spanning tree place each port in either forwarding or blocking state, although rapid spanning tree calls the blocking state the discarding state. But essentially, you guys understand what the function of that port state is doing, right? You guys already learned that, right? So you guys are probably wondering, hmm, what is the difference, right? What is the absolute difference, right, of rapid spanning tree, right? What is the improvement, okay? And that improvement, right, falls on one word, convergence, okay? Right? So if you read your CCNA, right, and you take your time, right, and especially in our last session, we talked about those timers, right? Hellos, right? Max age, right? We've talked about a lot of them, right? We talked about forward delay, right? And so if you guys read back, right? If you read back on those timers, right? I'm going to create a scenario, right? And so if you guys think about it, right? If you guys think about it, right? If a right, and I'll go ahead and show a topology just so it can make sense, right? Let's say, we connect three switches. They connect fine. They go through the tiebreaker process. They choose the root switch. They choose the root port. They choose the designated port, right? On the same segment has two non-root switches, right? They choose the designated port and they choose the blocking port. Perfect, right? But what happens, right? What happens when we have a failure on a link, right? What happens when we have a failure on a link, right? So if you look at the diagram, right, you have a root port, right? Root port, for some odd reason, right? The cable was eaten by rats, right? And so now we have no connectivity between these two switches, right? Switch three, now's root port is disconnected, right? So from a technical standpoint, what does this mean, right? If we go back to what we learned about timers, right? Switch three is not going to instantly know, hey, I had a failure. What do we need to wait for? We need to go ahead and wait for the timers, right? And that timer that I'm specifically talking about is that max age timer, okay? Right? And what is that max age timer, right? As a, as a refresher, that max age timer, right, is that timer that is waiting, right, is waiting for hellos, right? That time limit for hellos, right? Which is, of course, three times the hellos in spanning tree. And if it does not receive enough hello before that timer expires, then spanning tree will begin its algorithm again, perform that computation, then go ahead and begin the algorithm to, of course, try to find a new root port, decide on where I'm blocking at, et cetera, correct? Right? So let's talk numbers, right? So in the terms of convergence, if that link fails based on this diagram, we have to wait 20 seconds, right? We have to wait 20 seconds first for it to converge, right? To say, hey, we have a failure on that link, right? Now, right, we also have to wait for the two states to process. Those two states I'm talking about is the learning state and the listening state, right? And each of those states are 15 seconds each, right? That forward delay, okay? All right, so 15 plus 15 equals 30, right? After, of course, it goes through those states, it's finally in a forwarding state for those interfaces, right? Once that happens, right, we can go ahead and determine it took 50 seconds for this network to go ahead and converge, right? So, you know, people that, of course, that was using equipment of Cisco's knew that was too long, right? Right? How much of an impact that is, right? Well, maybe you have a data center, right? And this happens, right? A link breaks. 50 seconds can really determine if, maybe some build jobs are processed, right? And they're not processed in that 50 seconds, right? And a company just lost $1 million, right? So we can't afford 50 seconds of convergence. So the people back in, the IEEE, right? They went ahead and said, let's go ahead and improve on spanning tree, right? 802.1d, right? And let's go ahead and make an addendum, right? Make an addition, right? And create and define what rapid spanning tree is, 802.1w. Guys, don't take into heart, these numbers that I'm spilling out. You do not have to remember this for the exam. The biggest thing you need to remember is, of course, the function and the foundational topics of how rapid spanning tree and spanning tree works. Okay, so that is the reason why rapid spanning tree is here, right? It's killing off, right? It's killing off roughly 30 seconds of convergence, right? That's what it's doing, right? To go ahead and converge faster. All right. So with that being said, right? Right? What else is a couple of things that we need to know about rapid spanning tree, right? RSTP, right? They add a mechanism by which a switch can replace its root port without waiting to reach a forwarding state. I told you guys, right? Rapid spanning tree is eliminating, right, those different states, listening and learning what have you, right? We're immediately jumping, right, to a forwarding state, right, in certain conditions, right? Right? Rapid spanning tree adds a new mechanism to replace a designated port without any waiting to reach a forwarding state in some conditions, right? Right? And rapid spanning tree also lowers waiting times for cases in which rapid spanning tree must wait for a timer, right? So we're killing that. We still have those listening and learning states. I want to correct myself, but we're not waiting for the max age timer to expire, right? There's now a new mechanism, right? That the RSTP switch is now saying, hey, it's sending messages to its neighboring router to inquire, right? To say, hey, is there a problem, right? I'm not going to wait on the max age timer. Is there a problem within the topology, right? And it's going to go ahead and get a report. Then it's going to go ahead and act on it rather than waiting those 20 seconds. Okay. All right. So let's talk about some of the port roles and, of course, its function and how it works, right? So a couple of things changed, right? We still have the root port. You guys learned what that is. A new port role, right, is an alternate port, right? And what it is, right, that's a port that replaces the root port when the root port fails. Okay? All right? You guys know what a designated port is, right? Switch port designated to forward onto a collision domain, right? Now, a new port role, an additional port role, is a backup port, a port that replaces a designated port when a designated port fails. Okay, all right. And of course, last but not least, we have a disabled port, a port that is administratively disabled. What this means is that, of course, you went into interface configuration mode and you put in the command shut down, right? To, go ahead and say, hey, I want to go ahead and turn off this port. Okay. All right. So let's talk about, how does a switch become an alternate port, right? So to be alternate port, both the root port and the alternate port must receive hellos, right? They have to identify that same root switch. Okay. Right? They need to go ahead and do that. That's the first thing. That's the core foundation of how that works, right? And so basically what it is, right? That alternate port is exactly what it says in that term. It's an alternate port. It's a second best option for the root port, right? The alternate port can take over for the former root port, as quick as possible, right? Without having to wait for the states, right? Wait for these RSTP states to go ahead and transition, okay? So, for example, right, when the root port fails, right, or from a technical standpoint, when hellos stop arriving on the root port, right, the switch changes the former root port's role and state, right, the role from root port to a disabled port, right, and then it'll go from forwarding to discarding, right, which of course is equivalent to STP's blocking state. Then, without waiting on any timers, right, the switch changes roles and states for the alternate port, right, to go ahead and be the root port and to be in the forwarding state, right? And again, the key thing that you guys need to remember, right, is that with the alternate port, this, after it has converged into being a new root port, it doesn't need to spend time trying to figure out, go into different states, listening and learning and what have you. It doesn't need to do that. It immediately, because remember what I told you guys, it's certain conditions, it immediately moves to the forwarding state. Okay, because this is the purpose of what the alternate port is in place for. Okay, right? So as you guys see, right, we have switch 3, right? Link between switch 1 and switch 3, it fails, right? A rat ate the cable, right? Right? So gigabit 0/1, right, which is switch 3's current root port, right? It fails, right? But gigabit 0/2, if you guys look at this diagram, right, is the alternate port, right, in this topology, right? Switch 3 and switch 2, right? They're exchanging, RSTP messages, they'll BPDUs to confirm that switch 3 will now transition its former alternate port, gigabit 0/2, to be a root port, right? Right? And so what is switch 2 going to do after that happens? It's going to go ahead and flush its MAC address table, right? Flush all its entries. It's going to go ahead and clear it, right? And so now, right, after that happens, switch 3 is going to go ahead and say, hey, gigabit 0/1, I'm going to set your port role to disabled, right? And of course, go ahead and be blocking, right, has the state. And I am now instantly after that set gigabit 0/2 port role to go ahead and be a root port role, right? And of course, I'm being forwarded, right? Right. After it does that, switch 3 will go ahead, and switch to that forwarding state without going through learning, right, and listening, what have you, right? Why? Why is that the case? And I want you guys to understand this. It is because RSTP knows, right, the purpose of an alternate port. So it will transition the alternate port, right, without having to go to a learning state, because it knows what the alternate port role is, and it'll instantly switch it to a forwarding state, right? And set the role to being that new root port. Okay, right? And now this whole process, right, without having to rely on timers, as soon as the convergence completes, right, then forwarding instantly happens. So we're not waiting 50 seconds as we have, like how we have had to do in, spanning tree, regular spanning tree. Rapid spanning tree instantly transitions over. Okay, so this is good. This is good, right? I want you guys to go ahead, right? I want you guys to go ahead and take a look at this, right? Take a look at this, right? And compare these port states, right? Right? Disabled, discarding, right? Same thing, right? The port is administratively disabled, right? STP state, blocking, right? Compared to the RSTP state, discarding. Stable state that ignores incoming data frame and is not used to forward data frames. You guys already learned this. The terminology is just changing, right? STP state, right? Listening, right? RSTP state, not used, right? Because that's what we're taking out. We're killing off 15 seconds as well, right? We're killing off the learning state, right? That doesn't exist in rapid spanning tree, right? Now we go ahead and go to learn, right? Interim state with Mac learning and without forwarding, right? Right? You guys learn this. It means the same thing in both flavors of spanning tree, right? Forwarding, self-explanatory, right? So you guys understand there's just a couple of changes, right? A couple of changes of how it works, some terminology. So I need you guys to go ahead and read the theory so you guys can understand that, right? Okay, right? So we'll go ahead and stop here, right? And next week we will continue, because again, I want to take my time with spanning tree. We will continue discussing rapid spanning tree. All right. You guys have a great day and a great weekend. Thank you.